Nice. All right. So 18. All right. So let's me. What am I doing wrong here? Ah, there we go. Let me jump to that question. All right. So let me call up the questions. Okay, here we are. Let me scroll down to chapter 18. Let me go to 55. And sadly, these are really, I guess when I do 100%, maybe that's not too bad. I was going to say the photocopy is really bad here. All right, but I'll read this one. It says 2 wires are welded together end to end. Okay. The wires are made out of the same material. Oh, but the diameter of one is twice that of the other. So I'm going to do something like this. Maybe I'm going to just kind of do this first wire, and then that's welded with a second wire with twice the diameter. But I kind of see what might be coming here. If we make some waves on this stuff, then let me say the thinner wire has a mass density of mu. Then something with twice the diameter has 4 times more material and therefore 4 times the mass density. Again, because the volume, maybe I'll think of this first wire as a cylinder, but the volume of a cylinder, remember, is pi r squared times its height, or I guess when you lay it this way, you might call it its length. But my point here is if right here they say one has twice the radius, or they actually say diameter, but twice that diameter, then you're going to have 4 times more volume, and it's the same material. So they're really saying it's the same density per volume, but again, it's just fatter, and because it's fatter, it has more mass, and more mass, how much more? And it's 4 times more. Okay, so I suspect that's going to be quite relevant. All right. But the diameter of one is twice that the other. They are subject to a tension of, okay, so they're being pulled with a tension of 4.6 newtons. The thin wire has a length of 40 centimeters, okay, and a linear mass density of 2. Oh, okay, so I can put a number here, 2 grams per meter. So 4 times that is 8 grams per meter. Okay, so I actually know these numbers. The combination is then fixed with both ends and vibrates in such a way that 2 antinodes are present. All right, so if I were kind of drawing a picture, maybe there's a wall over here and a wall over here, and they're kind of connected here. Okay, and it's gonna vibrate, and I hesitate to draw anything because they have different densities, but maybe I'll do a rough drawing right now. This won't be my final drawing, but they say the combination is fixed both ends and vibrating such that there are 2 antinodes. So I'm going to put a node here. It's okay. It's going to arc up at one instant in time. So this would be the antinode, and then arc down. And this would be an antinode. Okay, so we've got 1 node in the middle, got a node on each end because they're fixed. So you might say we got 3 nodes here, but there's 2 antinodes. Okay. Combination is fixed at both ends and vibrates in such a way that 2 antinodes are present, with the node between them. being precisely at the weld. Okay, now I'm going to draw a little better picture on this one because I kind of drew a picture that would really be representing of a wave that was the same tension and the same mass density all the way through. But we know that for this one, that's not the case. We've got a fat section or a thicker section and a thin section. So let me just put maybe in the margin over here some other equations that are real important. One of them is wavelength is equal to velocity over the frequency. And the other one is the velocity is the square root of the tension over the mass density. And so I want to talk about these two equations and the consequences it would have on this weird wire, this wire that goes from one density to another, which now I can see why it's way up here at number 55, and I can see why you guys are asking about it. There's a complication going on because, see, the one with the smaller mass density, so the thinner one, has a higher velocity. And then the higher velocity is going to have the bigger wavelength. But they're hooked together, so they're going to vibrate with the same frequency. And they're hooked together, so they're going to have the same tension. So of all these variables up here, the two are hooked together and they have the same tension and the same frequency. But they do not have the same mass density, which means they don't have the same velocity, which means they don't have the same wavelength. So if I kind of put this in the same order where I have thin one, this would tell me that thin one has a longer wavelength than fat one. Okay, so a better picture would be something that looked like this for the thin one, then like this for the fat one. I'll even draw the fat one with a little more thickness. Okay. So I think that's really going to be one of the major keys of this problem, is to realize that they don't have the same speed and hence they don't have the same wavelength. Now, I think I read here, the combination is fixed at both ends and that the two antinodes are present with the node between them precisely at the weld. So yeah, so it didn't have to come out to be precisely this way. We just had to have one with a longer wavelength than the other. In fact, we know mathematically what it will come out to. We haven't done it yet, but we can work on the math and this fact that, you know, this one's 4 times bigger, but it has to do with the square root. So there's this square root of 4 is 2. So there's a 2-to-1 ratio in the size of these wavelengths. And we'll do those numbers in just a second. But this beginning part, I was just trying to get a good picture of this. Okay. Because of course they also said that this length is 40 centimeters. Okay. And of course, from node to node, that's a half wavelength. So I guess as I kind of am getting an understanding of this problem, and I haven't even got to the question yet, I would say that the wavelength is 80 centimeters here for this thinner of the two wires. Okay, so finally now I can get to the question. The question says, what is the frequency of vibration? All right, so since frequency is velocity over wavelength, and as I just reasoned out, the thinner wire, just so my focus just on the thin wire, has a wavelength of 0.80 meters. And the velocity is the square root of the tension, 4.6, over the mass density. That's this equation here. And they told me that was 2 grams. I'm going to write it as 0.002. See, that way my tension in newtons and my mass in kilograms per meter workouts, hopefully beautifully. Let me call this page 1 and migrate on to page 2 here. But maybe I'll just kind of check my units here. This Newton would be a kilogram meter per second squared. And so when I divide it by a kilogram per meter and take its square root, the kilograms cancel. This meter moves up to there when you flip, and I get meters squared. Take the square root of that, and that becomes meters per second. And then on the outside, I have a 1 over meter from the wavelength, which is going to cancel, and we're going to have just 1 over seconds, which equals a hertz, which is what we're trying to solve for, the frequency. Okay, so the units work out great as long as I, stay in SI units. So that's why, even though they gave me the mass density in grams per meter, I put it into my little formula as kilograms, figuring that would be, the requirement, and I just check that with the units. All right, so my units work out great. Now let me just do the numbers. So square root of 4.6 over 0.002 should give me the frequency. So grabbing my calculator, and I get 4.6 divided by 0.002. Take the square root. I guess that's 47.958. Divide that by 0.8. And we're looking at a frequency of about 59.9 hertz. Okay. And they both have that same frequency because they're hooked together and vibrating together. So that's the frequency of the thinner one, but it's also the frequency of the thicker one. And that's why I think the question just says, what is the frequency? Oh, you know what? I needed to write down chapter 18, number 55. So when I send this recording out, know which one is on there. All right, and then the other one, B says, oh, what is the length of the thick wire? Well, maybe using the same equation that we just did, which was frequency equals, and I'll say it's 1 over the wavelength times the square root of the tension over the mass density. I can now get the wavelength from this because the frequency is the 59.9. The wavelength is unknown, but again, because they're tied together, the tension is the 4.6. And then, of course, the mass density, as we mentioned earlier, is 4 times greater. So that'd be 0.008. So the wavelength would look like this, 1 over 59.9 square root of 4.6, 0.008, and grabbing a calculator. 4.6 divided by 0.008, taking the square root, then dividing that by 59.9. Looks like I got a wavelength of 0.40 meters. Okay. Now, again, coming to our picture, and I'll bring it back into the screen. This thicker one right here, this length of it, this is a half wavelength. So I guess I would say the length of it is half its wavelength. So 1/2 of 0.4 is 0.20 meters or 20 centimeters. And not really a surprise, given that we've got these squares and square root going on. See, this one here went up by a factor of 4. in its mass density. And then when we took its square root, that's a factor of 2. So its speed went up by a factor of 2, which means its wavelength would have, or the difference between the, from big one to thin one is a factor of 2. So this should be twice as big as that one. So 20 centimeters would be the square root of the 4 times bigger. Now, nice. That helped.
Thank you.
All right. There's a good one for us to start this morning.
I have a quick question about that problem.
Yeah, fire away.
Would there be any sort of reflective effect at the weld joint there? Because I remember you saying in one of the lectures, whenever you have a change in, I think, density because of the change in inertia, it would cause a reflection.
Absolutely.
Okay. And that doesn't interfere with the wave motion as in the smaller part?
Okay. Yes. However, this is the key. What you say is true, and we can start talking about what we call a double resonance situation, a little beyond the level and the scope of this class. But that was all considered when they described the pattern.
Oh, okay.
So they described the pattern that I had 2 antinodes and that the weld joint between them was a node. And so maybe I'll come back to this first picture. This picture where I have a string with the same density, what's happening is the wave goes down, hits the wall, and reflects off. And then, of course, it goes down this way, hits, and reflects off. And so we have reflections only at the endpoints. But what you're saying is a more complicated scenario, and that's exactly what we have, is we would go down here and 100% would reflect. Then it would come down here and part of the energy would reflect and part would transmit. Mm-hmm. Then it would hit this wall and 100% reflect. It would hit this joint again, and there'd be a partial reflection and a partial transmission. And so it's pretty complicated what's going on, and the amount of energy would depend upon that change in density. However, the pattern that is eventually set up would then, in this case, would be described, and this is how they described it, that you would have it such that this is a node.
Okay.
If the amount of energy reflected at this joint was different than the way they described, you may get something that looks like this. You may get something that comes up. Then the thicker one starts. And the node's right here. So it's not an automatic requirement that the joint be the node. The mass density was an automatic requirement that this be twice the length of that one. But the amount of energy that gets reflected here is part of what you're saying determines where this node is going to be. How much energy is trapped on this side of the weld and how much energy is trapped on that side of the weld. And trapped probably a wrong word because it's partly reflected and partly transmitted. So this could actually be a really complicated problem, but the reason I didn't have to give that thought about it is because they gave me enough information to say that this is the node and the node is at the weld.
Okay, cool. Thank you. That makes sense. And then because it tells you have 2 anodes, that's how you know it's only got those 2.
Yeah, exactly. Yeah. And So this antinode is here. Yeah, right. Yeah, exactly.
I had one more quick question. If you were to have like only one node, what would that look like? It just looks like straight across, or
Now, do you mean one antinode?
maybe I was getting confused at one of the lectures, and um, you were going over how the value of n could equal one through however many, and you demonstrated this. I think you said this would be one node, or maybe it was one anti-node. It must have been one anti-node, just that
Well,
single arc.
I got to admit, there's always a little bit of confusion because the ends are tied, so they are nodes. And since they can't be anything but nodes when you tie them, there's always a debate, do we count them as our nodes?
Oh, okay.
Okay. And if the answer is yes to that, then we start with two, and then we can have two or three or four or five or six, but we can never have one node. If we don't count them, then one node would be right here, and we would have something that looked like that.
Okay. Okay, yeah, that answers my question. Thank you.
Okay. And I could be wrong here, but I kind of got the impression you were even asking about this, that, okay, what if I just had one antinode? Now, a string with the same density would have the same wavelength. It would look like that. And then this part right here would be the antinode. And so a moment later, it would look like this. Now, for this scenario, something that had just one antinode would look maybe something like this. Let's see. We have to have the thinner one with a longer wavelength, so it would arc like this. Shoot. Let me draw that again. And so maybe I'll put this mark right here. So this half of it is twice that one. And so it would look like this for the thin one. Look like this for the fat one. And they would each represent, then this would be a quarter of a wavelength, and this would be a quarter of its wavelength. But its wavelength is is half of that wavelength. And then so this thing would vibrate back and forth in this kind of weird looking shape. But the key is we've got to have a 2-to-1 ratio in the wavelength because of the mass density piece of it. Yeah, and right. You're actually, this is really good. This is the kind of thing that we would do next if this was not like a mini class introduction to waves. If this was a whole class on waves, then we would say, okay, what about this boundary? How much energy is reflected? What kind of other patterns could we have? This could get real complicated real quickly. And that's kind of what I was saying for this class. The good and the bad is the bad part is we've just done enough to really get into some really tough and interesting problems. But we're going to leave them. And then that's also the good news. We're not going to get to the tough ones. We're going to start over with some easy stuff in thermodynamics and move on to another topic. And so if your education takes you where you have to take an upper division class on waves, you'll spend a lot more time talking about the amount of energy that is reflected at that weld point, and then what kind of patterns could happen. And even more complicated waves where the mass density is a continuous function that changes throughout. So those are really good scenarios and realistic scenarios that got to be taken into consideration. All right, but let me take this as an opportunity to, and suppose I should jump over to solutions. That one felt pretty straightforward. But let's see, they got 59.9.
I have a quick question.
Yeah.
I'm from Physics 102.
Oh, good.
I had a question on the homework. The first couple weeks, I didn't have any paper at my house, so I was just doing it all on a Google Doc. I know in lecture you like describe it, you want it written out. Do you want me to write it out, or can I submit my Google Doc?
Oh, your Google Docs is fine. I have no real structure. I like to say this: the homework is a learning exercise for you. Okay, so whatever works for you. I would say that given the nature of physics, and given that, other than this pandemic, you've learned, by doing pencil and paper. That's what I just recommend. Just keep doing it by pencil and paper, and make a PDF out of it and submit it to Canvas. But if you did it on any other medium, it doesn't matter. It doesn't matter what the medium is. I just want you to work through it and turn it in. Again, the whole point is to get you to practice problems and get ready for the test.
Okay. And then I had another question on the test. I know it's on the 11th at our scheduled class time. Are we do we just all go on at that time and take the test, or how does that work?
Yeah. So I'll say more about it this Sunday when I send out the week thing, because your test is the 11th, right? Yeah.
Mm-hmm.
And so for you guys, you're going to just log into Canvas, and then and you can even go there now and click on the exam. Although when you do it, you'll see it says locked until 12. So your class is 12:45. So it'll say locked until 12:45 on February 11th. So at 12:45 on February 11th, you click on it, and just however you want to do it. If you still want to use your Google Docs, you can. I recommend that you just take an old-fashioned pencil and paper and just go, hey, and just start, read the first one, answer it. Read the second one, answer it. And I'll tell you, I haven't explained this quite yet. By the way, let me just write down the time. 10:41, 102 questions about test. But go ahead and, do the test however you want. The first half of it is multiple choice. And usually I tell the students just, take the piece of paper right here and put one, just write out number 1, A, number 2, B, number 3, C, number 4, D. And you can just write it in. And then,
okay.
And then the second half of the test is going to be like your homework problems, where you read it. It'll say something like, a ball is dropped from rest. How far did it fall after 3 seconds? And so you just work that out and give me an answer. And then what you're going to do then is just turn in this pencil and paper worked out.
Mm-hmm. Okay, sounds good.
And more directly, your question was, does everybody do that? And yes, there are some exceptions. If people have a valid time conflict, I'm more than happy to work around that. Obviously, things are important, like keeping a job, and so some people are working full time, and I get that. But I would like to have everybody. It's not possible, but I'd like to have everybody at start at 12:45, finish at 2:30, and inevitably there's a few questions, and so I'm at the end of the email chain, and just shoot me an email and says, hey, I number 7, did you mean mass of the ball, or did you mean the mass of the earth? And let me answer that.
Got it. That's all the questions I have. Thank you.
Oh, no, you bet, Isaac. All right. And then that was you in the chat, right? Okay. I'm
That
from
was.
102, and I had a couple quick questions. Yeah. Okay. Good. All right. And let me mention again, anybody out there who is from 102, you guys have priority right now. And I want to get to yours first. And so let me scan the whole chat room here. Looks like chapter 17, chapter 18. Can we do problem number 1 on the practice exam? Okay, so these look like all 123 stuff. So, all right, unless there's no other 102, let me put down the time of 10:45, and then let's go to chapter 17, number 53. It's like asked by Jake. Okay. All right. And so up here, I'll just put chapter 17, number 53, page 1. All right. And then let me come back to the questions and see what chapter. So we were in chapter 18. So I need to scroll up. So chapter 17. Oh, 53. Oh, so 53 looks like is the last one in the group here. Okay, good. Let me just read it here. So 2 ships are moving along a line due east. The trailing vessel has a speed relative to a land-based observer of 64 kilometers per hour. Well, I think I'm going to have some unit conversion things going on here. And the lead ship is 45 kilometers per hour. All right. So let me just draw a due east. And normally on a compass rose, east is the x-axis. Okay. I'll just go east. And it looks like we got a lead ship. And I'll just make a little triangle for my lead ship. And a trailing ship. Okay. And if I remember right, the trailing one was actually going a little faster. Let's see, the trailing vessel has a speed of 64 kilometers per hour. And the lead ship has 45 kilometers per hour. Okay. Now, what's important, though, is this is relative to the ground, a land-based observer. Keep that in mind. I don't know how that's going to play out here. The 2 ships are in a region in the ocean where the current is moving uniformly to the west. So kind of like on a river. I guess that's what things like the Gulf Stream are, right? They're rivers within the ocean. And this is flowing to the west at 10 kilometers per hour. The trailing ship transmits, sonar signal at a frequency of 1200 hertz. What frequency is monitored by the leading ship? Use 1,520 meters per second for the speed of sound in the ocean water. Now, one thing that I hope came across in this problem is these are waves, these are sound waves, but they're not sound waves in air. This is a sonar system. And so they're giving us sound waves in the water. And so this underwater speaker system, so a transducer, so would then make sound waves that then travel up to the lead ship. And so they are waves, but they're sound waves in water.
Would these be transversal waves?
No. Sound waves, you can't have transversal waves in water or air because if I put a bunch of molecules next to each other like this, if you take the first one and vibrate it longitudinally, it can bump the next, bump the next, bump the next, bump the next. So longitudinal waves work great in air, in liquid, in solids. But a transverse wave, that means you take this atom and you move it up and down. The only way an up and down motion can make the next molecule move is if they are bound together in some way. And so that works for solids, but it does not work for gases or liquids. So if you took a molecule and moved it up and down, it would not make this one move. And the truth is there would be a little viscosity, and so there'd be a little bit, but it would die away, and it would only go maybe a couple meters and be done. So we like to say that there are no transverse waves in gases and liquids, but only in solids.
Okay, yeah. I got my terms mixed up there.
Okay.
Yeah.
And it's also, as a side note, this is how geologists are convinced that the center of the Earth is liquid. Actually, and then the center is a solid, but I'll hold off on that. But there's a liquid ball in there because they know when you take the Earth, and there's a big earthquake here, and the waves go out.
Yeah, I think there was
all this
like this in the book.
Yeah, all the seismographs in what we would call the shadow of the liquid only pick up longitudinal waves. They do not pick up any transverse waves. And that's how they determine then the size of the liquid ball in the center of the Earth. Because you can't have the transverse waves in a liquid or a gas. All right. Okay, but back to this problem then. Okay, so maybe the first thing I should do is a little unit conversion. Let me get these velocities in meters per second. And let me just remind myself of the question. What does this say? The trailing ship transmits a sonar at 1,200 hertz. The frequency is monitored. Oh, what frequency is monitored? Now, all right, so hopefully what's going on in your mind right away is this is a Doppler effect. There is some motions going on between the source and the observer. It's even a little more complicated than that because not only is there a movement of the source and the observer, there is a flow of the water itself. So let's give that some thought. But before I go too far, I want to get some numbers that are in SI units. So let me take this 64, and if it's a kilometer, that would be times 1,000, get it meters. And then let me divide it by, instead of an hour, let me do the number of seconds that are in an hour. And there's 3,600 seconds in an hour. So let me write this as 17.8 meters per second. So that's the speed of the trailing ship. This is going to be the source of the sound. This is the one that has the hydrophone inside of it, and that's the transducer that's going to send these waves towards the lead ship. Okay, then here we have a 45, and then let me multiply by 1,000 to make it meters. Let me divide it by 3,600 seconds to make it meters per second. And so the lead ship is 12.5 meters per second. And then the current is 10 times 1,000 divided by 3,600. And that would be 8 meters per second. Okay, so there is my speeds. And maybe to get myself some new working here, let me then say, all right, I'll fold this over, page 2, and say, all right, so this is a Doppler effect problem. And the derivation of the Doppler effect said that there would be a new perceived frequency that would be affected by this motion. And so we worked out that if v is the velocity of the wave, then, and I kind of like to remember that frequency is velocity over wavelength. A moving observer would be like the waves are going faster or slower, depending on which way the observer is moving. So in the top is the velocity of the observer. And it would be a plus if I was moving towards the observer, and a minus if I was moving away from the observer. I mean, toward the source. And so the moving observer would then be the effect of making the waves traveling faster or slower. Like I said, if I'm moving into them, so if I am the observer and I'm moving towards my source, I would use a plus sign. If I am moving away from the source, so again, I'm the observer moving away from the source, that would be like the waves are coming at a lower speed. So I would use a minus sign. And so I like to write it this way. Use the upper sign when I'm moving towards the source and away. Now, the same thing is true, but for a little different reason, when the source is moving. And when the source is moving, you produce the sound here, which if you weren't moving would have made, a certain wavelength. And so if these are the crests, they're equally spaced. But if you're moving this direction, the second one is then a little bit closer behind because you moved closer to it before you emitted the second wave. And so with a moving source, you would have made a shorter wavelength. So you affect the wavelength. So a moving source would be affected down here in terms of the wavelength. And of course, if you're moving towards your observer, you would shrink up the wavelength. And if you were moving away, you would expand out your wavelength. So maybe I went into too much detail there, but that's how I remember the Doppler equation here. Of course, you guys are going to have an open book test, so you can just have your book open and look this formula up here. But that is what's going on here. And there is some relative motions here. And so what we are looking for in this problem is the F prime. We're looking for what does this leading ship hear? What is the frequency that they hear? Now, what I would call the true frequency, the honest frequency, the rate at which the transducer, that is the hydrophone on the trailing ship, is actually doing, that's this F. So the F is what you would say the real mechanical vibration. And they're telling us that this is 1200 hertz. So that's the real frequency. Okay. Now, here's where the problem gets a little interesting. And at first looks hard, but I'm glad you asked this one, because if you had, in this case, a current, or in the case, if this was in the air, you might have the wind blowing. How do you handle that? Well, here's the answer. The speed of the sound waves, whether we're talking about the speed in the water or in the air, this one we're talking about in the water, is relative to a stationary water. So if the sound went out, and if it was the wind was blowing or the current, it would still just go out from that point. So what I really need then in all of this, and in this little formula here, is I really need the speed of the waves in the water, but I also need the speed of the observer relative to the water and the speed of the source relative to the water. See, here's how I'm going to take care of this current. What I'm going to do is I'm going to come back over here to this trailing ship. This number that they gave me, the 17.8, this is the speed relative to the land. But with the water going this way at 2.8, I would say that if I take 17.8 plus 2.8, that is the speed of this trailing ship through the water. And that's what we care about. What is the speed relative to the water? Because these are the waves in the water. So what I'm going to basically be saying here, and I'll put it down here, the speed of my source, the object making the sound, is actually 17.8 plus 2.8. So 17 and 2 is 19. That makes 20.6 meters per second. So if I was just on this ship and I didn't look at the land, see, the land in this case could just confuse you. The question really is, how fast is this hydrophone going through the water? That's what's making the waves. All right. So that's the hard part, I think, of this problem is, what do I do about the current? And the answer is really not much, except for you really need to know the speed of your source, the hydrophone. You need to know the speed of that through the water. And the speed that they gave us, the 64, which converts into 17.8, is not the speed through the water. You've got it going that way through the land, but then you've got the current going that way. So you add the two together. That's how fast you're going through the water. Or maybe put another way. Let's say the ship was anchored. You would say, oh, it's not even moving. And you would say its land speed is 0. And that's true. But because there's a current going underneath the boat is just anchored there. But its speed is not 0 relative to the water. The water's moving. And so the water is moving at 2.8. So if you were just stationary, you would say your speed relative to the water is 2.8. What you mean by stationary is relative to the land. And maybe I'm spending too much time here, but that's the tricky part of the problem, I think, is to figure out what is the speed of the source and what is the speed of the observer relative to the water, because that's where the waves are. They're in the water. It has nothing to do with the land, has nothing to do with the air. And if these were sound waves in air, I would do the same game. I would say, what is the speed of the transducer in the air? And the wind could be blowing east. And so I would subtract off whatever the speed of the wind is instead of add to it. The wind could be blowing to the west at a different speed than the water wave. So whatever the speed of the wind is. So, well, I'll move on. And I hope I'm getting my point across here. Is that the way I'm going to handle a current or the wind is nothing special. I'm just going to use the speed of the wind together with the speed relative to land to figure out what is the speed of the speaker, or in this case, the hydrophone, relative to the water. So this is the speed of the hydrophone relative to the water. And I can do the same thing with the observer. The observer is moving due east at 12.5, but then the current, and that's relative to the land, then the current is flowing underneath it to the west. And so essentially the receiver on the lead ship is moving through the water with a speed of those two added together. So 12 and 2 make 14, and another one makes 15.3 meters per second. Yeah. All right. So now, when you view it this way, you could just simply put it into our Doppler equation. We don't need to worry about what's the speed relative to the land anymore. And we don't need to worry about the speed of the current relative to the land anymore. Nothing is relative to the land anymore. We don't even want that. The waves have nothing to do with the land. The waves have to do with the water and the two ships. Those are the three things we need. The speed of the waves in the water, the speed of the lead ship, the speed of the source, which is the trailing ship. All right. So now I can put these numbers in here. So this says take the speed of sound in the ocean water to be 1,520. Okay, good. In the numerator here is the speed of the observer. So this is the 15.3. And in the denominator is the speed of the source. It was a little faster, 20.6. Now we got to watch our sign. As we said, let me do the top one here. We said that if you're moving away, and of course, the observer is moving away from the source. Come back to the picture, right? Here's our observer. Observer is moving away from the source. If you maybe thought of the source just sitting there, not moving itself, we're definitely moving away from it. All right, so the away is the minus sign. The away would make a lower perceived frequency. Okay. On the other hand, the source, so the trailing ship, if you kind of think of maybe the lead ship just sitting there, you would say it's moving towards it. You know, it's trying to get to it. So I would say in the denominator then it's towards, that would be the upper sign. So we would have a minus there. All right. So again, like all of our Doppler problems, we just need three velocities. This one is a little harder because they gave us speeds relative to the land, and that's just irrelevant. We want speeds relative to where the waves are. The waves are in the water. So fortunately, they gave us the speed of the water relative to the land as well as the speed of the ships relative to the land. So ultimately, I can get the speed of the two ships relative to the water. And I could also then look at my picture and then decide, well, which way they're moving. All right, so finally, let's see what we get here. So if the numerator is 1520 minus 15.3, and I divide that by 1520 minus 20.6, I get a number that is a little greater than 1. Okay, so it's going to shift the frequency up a little bit. Let me multiply by the original sound of 1200, and I get 1,204 hertz for the perceived frequency from ship number 1. And that was a good problem. So let me check that. What was this? So let me go to solutions, chapter 17, number 13, and they got 1,204 points, and they do a 0.2. Okay, 0.2. Why not? Yeah, good. Got it right.
I had a question. Why is it that we don't have to, or why is it that the speed of sound through the water is unaffected by the current?
I guess I'll do this kind of mental picture. Let's just say you took a boat out to the ocean, and it could be the California currents. Yeah, I'll do the California current since we're in California, but the Gulf Stream is much stronger, so I kind of like that one. But anyway, let's say you take a boat out, you go out past the islands, you're just kind of hanging in there. So here's your boat, here's the water, and you know, let's just say there's a piece of seaweed kind of floating in the water right there. What you may not even realize is that relative to the land over here, you and the seaweed are kind of moving along. And the molecules that make up the water are moving along. From your perspective, from the molecule's perspective, from the seaweed's perspective, you don't have any motion. You're just, you know, there's nothing going on here. If you made a sound wave, so you maybe you put your hand and you splash on the top and maybe try to attract dolphins or something. Okay, flap, flap, flap. You know, the sound waves go out equally as they bump into each other. Now, here's where I have to be careful. They go out equally as they are moving along in this direction. So someone on the land may get a different view of that. They say, oh, well, you started the sound here, and then your second clap was here, and your third clap was here. So, you know, they're seeing something that looks like, you know, the first clap, the sound goes out to here, centered. Oh, it's a terrible picture. I hope you kind of got the idea that the perception from the land would be as if you're moving. I get that. But I guess what I'm really trying to say is the bumping of the molecules is really what sound waves are. And so from the perspective of the molecules being at rest, they would go out equally. And so we want to take that perspective. And they wouldn't be affected just because they're moving. In the same way, they wouldn't have been affected if you would have said the water was stationary and then somebody in an airplane is flying by looking at it. That the flying airplane, that motion doesn't change that these go out equally. And if all the water moves out, you know, equally, that's just from your perspective. That's from the land's perspective. But from the molecules itself, there's no motion going on. They just bump equally in each direction as they move out. And so I guess I'm trying to say it's all speeds are relative. And our Doppler effect is set up to measure things from the molecule's perspective. A fancy word is from the medium's perspective. There's nothing magical about the land. And, you know, because somebody else could watch it from land, somebody else could watch it from an airplane flying overhead, somebody else could be in a spaceship, somebody else could be in another solar system. But they see it go out equally from a reference point of no movement of the molecule. So you got to kind of get in the what we call the reference frame of no motion of the water molecule.
Cool. Thank you. Makes sense.
Hope that helped.
Yeah, it does.
Okay. But it's also a nice little trick because you could have, you know, wind blowing, and these could be sound waves, and it sounds like it's going to be a hard problem because the wind's blowing, you know, or in this case, it sounds like it's going to be a hard problem because the current is flowing. But really, all of that is relative to some other point, and stop that. Get out of this land view or airplane view and just get to the three things that matter: the medium where the waves are, and the source, and the observer. Nice. Okay, let me move on then. Those are some good ones here today so far. And then
I have a question.
Yeah.
Is this class, which class is this?
Oh, well, what I'm taking questions from anybody who asks it, but I'm giving priorities to those in 102. Are you in 102?
Yes.
All right, let me take your question then right now.
All right. I already finished my lab. I finished my graphs and I finished my table and everything, my calculation. But I am having some little problem. This is my first time taking a class like this. Having problems with my discussion page.
Oh, okay.
So far I can tell you what I got, but I don't know if I'm right, and I don't know exactly what is that you want, because in the first question is describe the shape of your distance time graph. So I answer the shape of the distance time graph is a curved line.
Yes, and that's fine. Let me do you one better. You wouldn't know this, okay? So no fault of your own. You won't know this until you start reading the other questions. but there's really two things they want you to notice about that line. The first one, it's curved. That's good. You noticed that.
Yes.
They also want you to say it's curved upward.
It's curved upward.
Or what we would call in a math class concave up. So it looks something like this, right?
Uh-huh.
Yeah. And so they, hang on, I just want to write down my notes here. So lab questions. Okay, so they want you to say, and you'll see this in a second as we go through these questions.
Yes, yes.
They want you to say that it is a curve. Okay, so, all right, curve. And it's curved with what in math we would call a concave up.
Okay, concave up. Okay, yes.
As opposed to curved like that, concave down.
Yes.
Okay, so it's not that.
Okay, yeah.
And you're going to see here that both of these observations are important as we go forward with the rest of the questions. So they're trying, they're trying to help you analyze your data. Okay. All right, so watch, go to question 2.
Okay. How do we interpret this slope of any distance time graph? That one I really don't know what to answer, because I think the way I interpret, I don't know exactly what you're asking, but I interpret that is accelerating. I mean, it is no, that is displacing, like it's changing in time. I don't know exactly what.
All right, good. Let me help you here. Here again, it's not trying to be hard, but let me see if I can draw you a picture here. If you were to be in a math class,
okay,
and you were to plot X and Y, and you had a curve that looked something maybe like this, okay, and you looked at part of the curve, maybe right this little section right there, and you called that the slope, okay?
Yes.
In your math class, you would have said this: the slope is the rise over the run.
Okay.
Okay.
Yeah.
Now, what we're doing is we're not plotting Y, we're plotting V.
V, okay.
And we're not plotting X, we're plotting time.
Okay.
So our rise would be the increase, or a better word is the change in the velocity. And our run would be our change in time.
All right.
Does that make sense so far?
Yes, yes.
Okay, one more step. Change in velocity over change in time was our definition of acceleration. So the answer they want you to give when they ask, what does the slope tell us? The answer is, oh, it tells us the acceleration.
Okay. So that's what you want.
Yeah, so you can just give one word. It's acceleration. That's what it gives us.
Okay.
And so the answer is not long. It's not actually real important. Here's what's important. Did you see how I took my previous knowledge from math and applied it to what we're learning now and came up with a conclusion?
Yes.
All right. Now watch this. Go to your third question. The third question then says, if I remember right, says, what does your speed time graph tell you? And you have something that looks like this, right?
Tell us about the falling body. So my answer was that. Sorry. Yeah, my answer was that it tells us if it is accelerating or decelerating. So
I owe you an apology. I got ahead in your discussion questions. Let's go back to number 2.
Yes.
I'm sorry. You're going to see that that's going to be the answer to another question coming up.
Okay.
Okay. My bad. Your second question was a plot of position versus time. So it wasn't change in velocity, it was change in distance.
That's what okay.
Yeah, I'm sorry. And it looked like you wanted to ask something there. And I apologize. You should have.
Yes.
Okay. So let's come back to question number 2.
Yes.
It's change in distance with time. And that is called velocity. So that is the answer for number 2. The slope gives you velocity.
Okay, the slope gives you velocity. Okay.
Yeah.
And number 3?
Okay, so, right. So let's come back here to number 3. When you look at your graph that looks something like I'm trying to draw here, distance and time, and the slope is small at first, and then later on gets big. So this graph tells me that I go from a slow speed to a fast speed. That tells me it is accelerating.
Okay.
And that's really the answer you can give for number 3, is just say, oh, when I look at that graph, here's what I see. I see it as proof that the object was accelerating.
Yeah, okay.
So
yeah.
Again, my apologies. I'm going to just recap the first 3 because you were supposed to get out of this, and I screwed it up, that there is, they go together. The first one says you have something that is curved.
Okay.
That means the slope is changing.
Uh-huh.
And it is concaved up, so that means the slope is getting bigger.
Okay.
See, so that's what we're going to need to answer number 3.
Yes.
Then, of course, question 2 is having you focus on the slope. The slope would give you the velocity.
Yes.
So in question 3, you're supposed to say then the velocity or the speed is slow at first and then goes faster, and that's accelerating. So those first 3 questions, you're supposed to come to the conclusion that your graph is telling you that the object is accelerating.
Okay. Okay.
Right. So what we know so far is that the object is accelerating.
Yes.
Okay. And those 3 kind of went together. And the next 3 will go together. Let me do a better job on the next 3.
Yeah, I mean, for the third one, describe the shape of your speed time graph. Yeah. I feel that is linear, that is upward line.
Yeah.
Which is positive.
Right. Now, okay, and let me just say, when you use the word linear,
yes,
you are saying that it has the same slope, aren't you?
Yeah.
It's not like number 1, right? Number 1, by saying it's concave up, we were saying the slope got bigger and bigger and bigger.
Yes.
So what we're observing here is that the slope stays the same. And so we're going to do the same thing here, right?
So I mean that is constant.
So it has a constant slope, right?
Yes.
But okay, so question 5 is asking you, well, what does the slope give you? And so let me do the same thing here in 5 that I did in 2 and say, well, the slope is the rise over the run.
Yes.
And for this graph, though, and I said I didn't want to mess it up, and I already did, rise over the run. My apologies.
Yeah.
The rise is the change in velocity. The run is the change in time.
Okay.
And the definition of acceleration is exactly that.
Acceleration too.
So what the answer is for number 5 is to say the slope gives you the acceleration.
Really? Okay. Okay, that's interesting.
Okay, now, again, since I might have messed you up, let me just go back to question 2. In question 2, the slope gave us velocity.
Yes.
Because we were plotting distance versus time.
Yeah.
And then question 5, the slope gives us acceleration.
Oh, yeah, you're right. Yeah.
We're plotting velocity in time.
Yes. Okay, I got it.
Okay. So now if we put these 3 together, where number 6 is asking, what does this graph tell you? Remember, you said it was linear.
Yes.
And remember, you also said that the slope was the acceleration.
Okay.
And a line means it has the same slope. So you are saying that the acceleration is a constant value as Bob is falling.
Okay. Okay. One more thing. What time does this meeting finish?
Well, we do this. We go pretty much all day.
Uh-huh.
We start at 10 and go to 11:30. And during that time, we give you guys in 102 the priority. But anybody can ask questions.
It's because I have an interview with my transferring counselor at 11:30. So I might get out and then come back for the finish up the next. Can I do that?
Okay, yeah. So I was just about to say, good, because what we do is we at 11:30 we take a little break and we start up again at 12:30.
Okay, that sounds great.
Yeah. Thank you. Come back at 12:30. And then
by the way, I really love how you teach. I really love your class. Oh. Your videos, I mean. I really love your videos.
Okay. Well, okay. Well, thank you very much. All right. Okay. So, okay, I'll look for your name at 12:30 and we'll finish these. But let me say real quick before I leave you.
Yes.
Okay. So here was the point of the first 3. The first 3, you were supposed to come to the conclusion that it was accelerating.
Yes.
By looking at that graph. Yes. And then these next 3, you were supposed to come to the conclusion that the acceleration was a constant.
Okay.
And then when on the next question, and we'll do that when you come back, you are actually asked to calculate this slope because that's how you get the acceleration. So there's kind of 3 steps. Number 1, you prove that there is an acceleration. Number 2, you prove that it's a constant acceleration. And now we're about then to measure that constant acceleration.
Okay. Yeah. Sounds great.
All right. Yeah, go see your counselor and good luck to you.
Okay, bye.
All right.
Okay, bye. See ya. Thank you.
Hey, Dr. Young, could I ask a real quick conceptual question before we break here?
Absolutely.
It's about problem 9, and it's just actually sort of about the way to read the problem and get the material you need to answer it. Problem 9 in chapter 17.
17, okay. 17, 9. Oh, real long thing, yeah.
Yeah, so I mean, essentially, I understand how we're getting everything, but the way I read it, I got stuck on it because part A, I need to find the wavelength.
Yeah.
And I'm only given the frequency in megahertz.
Oh.
And later in the problem, it says 1,500 meters per second.
Okay, right.
I just started trying to do the problem and didn't read that.
Right.
Should I have been able to find, I need that information to be able to answer this first question, right?
Okay, yeah, you do definitely need the information. I suppose I could answer it in 2 ways. The first one is, yeah, it's probably good to make sure you always read all the way through a problem before you start it, because they might be giving you information at the end. Mm-hmm. I will tell you that when I read this the first time, I did exactly the same thing you did. Is I go, oh, and then they didn't give it to me. So what I did is I said, well, the human body is mostly water.
Okay.
So I just went to the chapter and looked up the speed of sound in water. And it actually came out to be, it was like 1497 or something. It was only 3 short.
Gotcha.
And then I did the problem that way. And then I got to the end and I go, oh, well, they're giving us to it. So
okay, cool.
I made the same. Sure. I made the same mistake. So I'm gonna tell you what you should do, but don't copy me.
Yeah,
totally. Should read all the way through a problem.
I just wanted to make sure I wasn't supposed to be able to find the velocity somehow, just given the frequency, because I didn't.
No, but you know what? I'm going to put a little plug in here for thermodynamics. I don't want to wear you out quite yet, but we do that a lot because your body is mostly water with other stuff in it, which is kind of like salt water. So if you just look up the speed in lightly salt water, you'll get it pretty close. And even if you just do fresh water, you'll be pretty close. Cool. And you watch this in the next chapter. I'm just going to head off a question you'll probably have. When we do our thermodynamics, sometimes they'll throw a cup of coffee out there and it cools down, or a cup of lemonade, cold lemonade that warms up, and they ask for different information. And most of coffee and most of lemonade is water. So they just use the numbers for water, and they don't say that in the problem. And that's always, students have always had a hard time with that. And I go, oh, just use water. And they're all like, what? But that's what coffee mostly is. I mean, you know how it's made. You just run water over the beans and a little bit of the stuff, the molecules in the beans come out. But something like only 1 in 1,000 molecules in there is something other than water, So,
cool. Makes sense. Awesome. Thank you.
Yeah. So that's a good skill to kind of learn here. All right. Well, maybe I'll take our break here, but I looks like we got some really good questions going here. I'm going to make a note of that. Where did we get to? We did some 102 stuff.
I think chapter 1827 was unanswered, and then physics review number 1 was unanswered.
Hey, hang on, Daniel. I'm just going to say chapter 17. I think that was number 9 I was answering for you, right? Ivy, Ryland. Okay, and then I'm going to put down, so I did what you said. I did 17. I hadn't got to yours, Hunter, which was 1827 in a 102. Can we do problem 1?
Yeah, Hunter typed into the chat that he left and he was hoping we could do 2718 when we start up again. So
okay, perfect. Okay. Yeah, we'll make sure we wait for him. Can we do there? Oh, there he is. The next session, head out. Yeah. Okay. Okay. That'll be the order when we come back. All right, everybody. Take a little break, stretch your legs, and use the restroom. And my case, get something to eat too, and I'll come back.
We're back at 12:30, is it?
And 12:30, yeah.
Okay, perfect. Thank you.
All right.